Hello and welcome back to the series. Today, I will talk about feature engineering in the context of machine learning. I'm building a ML pipeline in ML.NET C# for predicting if any goals would be scored in first halves. Here is a distribution of the halftime goals. So we have 90 matches without any goals and 151 matches with one goal and so on. This shows that my data is imbalanced, about 76% majority class. So if we sum this distribution from one goal to 7 goals in the first half, we get 76% of the matches. Sample of data, as you know from the previous videos, we have a CSV file of 5 columns. In the pipeline, the label is calculated like this: HT goals greater 0, which gives us a classification problem to solve. We don't care about the exact number of goals, which would be then a regression problem to solve, as I mentioned in the previous videos of this series. My goal is to maximize the reliability of the minority class prediction. HT goals is 0. So I want to focus on predicting this class, and this is really challenging. Everyone could simply write a pipeline to predict the majority class. And as mentioned in the previous videos, this could be misleading. So for example, if you get an accuracy of 75% when predicting the majority class, you would say, wow, it's above 75 or about 75%. This is very good because every accuracy over or above 70% is said to be good enough. But as you see here, even without a pipeline, even without machine learning, if you simply always predict that at least one goal would be scored, you get the accuracy of 76%. So if your model is not of a better accuracy than 76%, you simply don't need the model. And it's more difficult in this meaning or in this context to predict this minority class. So I say here, I want to focus on predicting this class. And in this video, I said it's about feature engineering. So how could I build my feature engineering columns? Which columns could we derive from the current the current columns? Is it possible to apply feature engineering with the odds? So let us concentrate on the odds. How could we derive some features? Explain how this would affect the training algorithm. Here is to mention, don't worry that I have forgot the I here. The AI can deal with this, as you know, I think. So this is a result from Manos. The report provides a comprehensive analysis. Let me make it bigger. So the report provides a comprehensive analysis and strategy for optimizing your ML.NET C# pipeline to predict whether 0 goals will be scored in the first half of a football match. The primary focus is on applying advanced feature engineering techniques to betting odds and addressing the significant class imbalance to maximize the reliability of the minority class prediction. Great. First, analysis of class imbalance. Your dataset exhibits a clear class imbalance. which is typical in sports prediction where the outcome of interest, in this case the minority class, is less frequent. The provided distribution is we have 90 matches without any goal and 20, 290 matches with at least one goal. The imbalance ratio is approximately 3, about 3 to 1. This level of imbalance means a model could achieve 76% accuracy by simply predicting the majority class every time. This is what I mean. You don't need a model, making standard accuracy an unreliable metric. Standard accuracy, it's said to be above 70. So if you build a model that gives you something between 70 and 76, this is unreliable in our case. As said, we even don't need a model to reach this accuracy. We can reach it without a model. To maximize the reliability of the minority class prediction, we must focus on metrics like precision, recall, and F1 score for this halftime goals class or for matches without a goal. So in this introduction, we take this here. We need to concentrate on precision, recall, and F1 score, not on the accuracy. 2. Feature engineering on betting odds. The raw betting odds are not optimal features. By converting them into probabilistic and market-related features, we can provide the model with highly predictive quantitative signals. Implied probability. Betting odds are a bookmaker's way of expressing the probability of an event, plus their profit margin. The first step is to convert the odds into their implied probability. Here is the implied probability. We divide 1 to the original odds. For your problem, the event of interest is under 5 goals, so under 3 goals, is the first half, which is a proxy for HT goals, either 0 or 1 or 2. Since your label is binary, so we solve a binary problem, this odds, the under 5 odds, are the most relevant. We will see that the pipeline is focusing on this odd more than the other odd over 5. So this is the first feature, implied probability. We derive it like this, 1 divided by the original odd. The second feature is overround. The overround is a built-in profit margin. It's calculated by summing the implied probabilities of all possible outcomes. For a simple two-outcome market, over-under, the overround this is the probability, also this is this one here. This is the probability of over odds and the probability of under odds, then -1. The overround can be a useful feature as it quantifies the market's liquidity and the bookmaker's confidence or risk assessment for that specific match. Third feature, fair probability or normalized probability. The most powerful feature is the fair probability, which is the implied probability after removing the bookmaker's margin. This represents the market's consensus on the true likelihood. Now, let us try it in Visual Studio. Here is the new class feature engineered data. that holds the new derived features from the raw betting odds. As a short recap, here is the old classification data structure that you know from the previous videos with the raw betting odds and our label. We still have the teams and the label in the new data structure in addition to the new four columns. So then the next mission is to fill these properties, and the code is here in the football prediction. We have our known method train classification models, you know from the previous videos, and I defined a new method build and train, which takes as a parameter the match data as I enumerable, and I will convert match data in feature engineered data. So feature engineering, step number one, I use a link, so I convert the match data in feature engineered data using link, using select method of link, and for each match data, I calculate the probability over, probability under, as said, 1 divided by the betting odds. And then I return a new instance of the feature engineered data. The label and the home team, away team stays the same as in the source, also in the match data. And here we fill the new features. So the over and under probability, and the other two features, the fair probability under, which is probability under divided by the sum of the probabilities, and we have the overround, which is the sum of the probabilities minus 1, as described in the suggestion of Manos, from the AI. Now we just need to call this method, and to make this symbol, I call it after the old code has been executed, so we can compare it in the console. And again, here a small recap what we have done in the previous videos. We load our data from the CSV file as a match data, and I calculate the distribution of the calls, and then I convert the match data to match classification data. So I convert mainly the number of calls in a Boolean property, which is true if any goals has been scored, and false if not. So and according to the distribution, about 75, 76 of matches have at least one goal. So the positive class is a majority class, at least here in our context. And the minority class is the negative class. So after we have our classification data structure, we load it again in a data view and then define our pipeline. We use one-hot encoding to convert the text in encoded text. This is how it should be done for categorical features. And then we define here that or we concatenate all the features we want to be considered in one column called features. So for now we have 4 features here. This is the raw odds. no feature engineering yet. And then we choose, for example, fast tree. And this here the plot the calculators just to get a probability of the predicted number. And after we defined our trainer, we use cross-validate with 5 folds. And this is where we output the metrics for each fold. I commented it out now for now. Here is the averages of the metrics. And after that, I call the new method for feature engineering and I output the metrics in the same way. Um, but and yes, and I use the same algorithm, no options, no hyperparametering, so we really can compare the output using the same algorithm and yet without any extra parameters for hyperparametering. And the same cross-validation with 5 folds. Let us give it a try. So evaluating fast tree model for any goals have been scored on row fitting the odds. And here is the evaluating of fast tree with feature engineering odds. So this is how feature engineering works. Now let us try another features. So could we, so the question is, could we enhance it furthermore using the other features? Let us give it a try. So now we have our teams and 2 features. And give it a try. So as you see, using 2 features in the same time, which are based on the same raw data, is not beneficial. We have we have here a downgrade. So what if we use only the fair prop under? So here we have um, also a better model. And what if we just use uh, implied probabilities? No, the implied probabilities is worse than the raw odds, at least in these 3 metrics. It's a little better in the accuracy, but as said, the accuracy uh, is here misleading. Any accuracy less than 76 is not reliable. We should concentrate on the IUC and or in the both of the IUCs. So this is not good. So I would say that only this feature is useful. So you see here we have um, enhancements in all of the metrics, also in the accuracy. So the message is don't mix too many features, especially if they are based on the same raw data. That's it for today. Thank you for watching, and I see you next time.